Welcome back to ECE 320A. We are working through Unit 10, which is dealing with Bode plots, and that material is discussed in Appendix E. And what we're trying to do now in the next few videos is to actually break the process down into some fundamental steps of sketching the Bode plot. And in this very first video of that set, we are going to actually look at identifying the different terms or factors in a transfer function. And really, you could think of these as flavors. And what we want to do is remember what we're doing to motivate this many-step process of sketching the Bode plots is we're trying to develop quick sketching strategies, and those will then result in two different plots: a magnitude plot, which is the magnitude in dB plotted with respect to frequency, and the phase plot, the angle of this transfer function as omega, the frequency, is varied. And one more thing to keep in mind is that we are presenting these strategies or techniques assuming that all of our poles and zeros are in the left half plane. And what we want to do in this, our goal in this particular video, is to first break or break up the numerator and denominator into particular factors so that we can determine what kind of factors we actually have. We should be finding a constant, we should be finding maybe poles and zeros at the origin, we'll maybe have real poles and zeros, and we'll maybe have complex poles and zeros. That's what we want to do in this video. So let's illustrate that. It's probably easier to think about this by looking at a concrete example. Suppose you're given a following transfer function, h of s, and you might just look at this very quickly and you can start to uncover some elements of this transfer function that can guide your thinking as you're sketching the Bode plots. First, let's look at the powers of s, or the highest power of s, in both the numerator and the denominator. In this case, the numerator has one s in it. It's s to the 1. That's a linear factor, or it's really just a first order numerator, so we would expect just 1 0 to appear in this transfer function. The denominator, on the other hand, is a fourth order. We have s to the 4th. There's now going to be 4 different values of s that cause that denominator to vanish. We should be expecting then 4 factors, or 4 roots of the denominator, which are 4 poles, and we now have 1 0 and 4 poles in this particular transfer function. To find the zeros, we need to factor the numerator, and the easiest way to factor that is to just pull out or extract the coefficient of the highest power of s. In this case, that's 4,000. And if we divide 400 by 4,000, I hope I've picked these numbers so that it's not that hard to do the math. We can see now that we have 4,000 times this factor of s plus 0.1. And now we can immediately set that s plus 0.1 factor to 0 to identify where the 0 is located. But we'll do that in a minute. The next step is to go ahead and factor the denominator. So now we can see actually that there is no constant term or no term in the denominator that is not multiplying s raised to the 0 power. We have an s, we have an s squared, we have an s cubed, we have an s fourth. So we have an s common to all of those factors. We can go ahead and factor that out. Now we have a cubic. We would then put that into MATLAB, put that into our calculator. We could graph it and try to find where at least one of those, if we have a cubic, we know that we now have at least one real pole, if we factor that out, we find that we have s plus 200 sitting inside that cubic. And once we factor that out, we can factor out a quadratic, which I'm not going to show that that leads to, well, I will subsequently, but actually that particular factor I've written using real coefficients, but it's buried inside that particular quadratic, and that's why we're writing it as a quadratic. It actually has complex roots. And the roots, the way I've written it, you can actually see those, and we'll discuss that in a minute. But the roots of this quadratic factor are at values of s equal to minus 6 plus j8 and minus 6 minus j8. And there's many different ways that you'll see this quadratic factor written. If we multiply it out, we'll see we have s squared. There's the quadratic piece, and you could then put this into a quadratic formula and find those roots of minus 6 plus and minus j8. We're now multiplying those out to produce a different form or structure for that denominator quadratic factor. S squared plus 12s plus 6 squared, which is 36, plus 8 squared, which is 64, and I've picked these to be nice or convenient. That's now 100, and 100 is actually a perfect square, and we'll get to that in a minute. But we could now rewrite that quantity s plus 6 squared plus 8 squared also as s squared plus 12s plus 100. And how we write it is really just how we want to use it or how we want to be thinking about it. In this particular case, we factored the numerator and the denominator, and this structure that I've now displayed for capital H of s, we will call that the pole zero form of a transfer function. And that will be in contrast to what we do in the next video, which is now to put this into a time constant form, which is where we now force all of our constants in our linear and quadratic factors to equal 1. And that will make the sketching of the Bode plots more convenient. But for now, to just think about where these poles and zeros are located, the pole zero form is a nice structure, and that immediately falls out once you factored the numerator and the denominator. In this case, we have a constant, which is from the pole zero form, and that's a different constant than what you would find as the constant in our time constant form. So just make sure that when I say, oh, let's now sketch the Bode plots constant, we need to make sure that we've already put the transfer function not in pole zero form, but in time constant form. But for now, we can think about this constant k bar being 4,000 in this pole zero form. Looking at the numerator, we're finding the zeros. Those are the values of s that cause the numerator to vanish, and those are upstairs. Those are the zeros, and I'm going to be calling upstairs and downstairs because that will actually determine the way that some of these pieces or component parts of the Bode plot actually slope. The zeros will produce upstairs slopes or slopes going up, and the denominator, the poles, will present or provide pieces of the Bode plot that slope downward. Here we have our zeros can be found by simply setting the numerator equal to 0. In this case, we only have the one factor, so we find that we have a 0 at s equal to minus 0.1 radians per second. And in this case, we then say that we have a linear zero factor, and that's this s plus 0.1, and it's linear because we have this s raised to the first power. And that's what we want to then be comfortable extracting from that numerator. We need to find these different or unique factors. If we look at the poles, we now, because s was common to all of those terms in the denominator originally, we actually end up with one of the factors, when we set that equal to 0, is in fact s equal to 0, and that's 0 radians per second, or dc. We'll be referring to that in many different ways. Or we could then say that we have a pole at the origin of our complex s-plane. That's what we're meaning by s equal to 0. We also had a pole at minus 200 radians per second, and that will be our linear pole factor in this particular transfer function. And we had the quadratic factor in the denominator. That was the s squared plus 12s plus 100, which through the quadratic formula gives us roots of that at minus 6 plus and minus j8, and this we would then call our quadratic pole factor. Our transfer function h of s in this example had a denominator quadratic, but we could just as easily have had a quadratic in the numerator, and then we would have had a quadratic zero factor. Let's look at this quadratic, because in fact that presents itself with a little bit more of a challenge in terms of sketching the Bode plot, but we're going to make in this class a simplification so that we can quickly, sort of on the back of an envelope, sketch these Bode plots, and if we want to, we can get a more accurate, precise Bode plot by putting it into a computer, running it in MATLAB. We can quickly find a Bode plot, but what we want to do is have the insight into how that might be sketched graphically by hand. So here's a little bit more background, and we're now going to hopefully connect where these complex roots now present themselves in that factored form that I illustrated before. Here's a little bit more background. We have one root that's in the second quadrant of the complex s-plane at minus 6 plus j8. I'm calling that s sub 1. And we have its twin, or its conjugate, or its cousin, however we want to refer to it. It's its conjugate. It's in the third quadrant of the complex s-plane. That now we just change the sign of the imaginary component, and so that's now sitting at minus 6 minus j8. And I hope you're actually trying to sort of visualize where these are located in the complex plane. We can pull all of the non-zero terms over to the left side of the equal sign, and we now have for the first term or root s plus 6 minus j8, and for the second root we have s plus 6 plus j8. And now I'm trying to get you comfortable with seeing that this particular factor on the left is the one associated with the pole in the second quadrant, and this particular factor, s plus 6 plus j8, when we solve that for s, that's associated now with the pole that's in the third quadrant, or at minus 6 minus j8. That forces that factor to 0. If we put these two factors together and multiply them out, that's what we want to do to try to find how we found this particular quadratic that we started with earlier. So now I'm just taking this yellow factor, the one on the left, and the blue factor, multiplying those together, and I will do that a little bit in an informed way. And now what I'm really trying to do is create that form that I had before, and to do that, let me now combine the s plus 6 into a subset and s plus 6 in the right as a subset, and now let me perform the multiplication so that I now have s plus 6 times s plus 6 plus j8 times the s plus 6. So now I've pushed that yellow factor of s plus 6 through both terms on the far right. And if I multiply now the minus j8 through the two terms on the right, I have minus j8 times s plus 6 and a minus j8 times a j8. And that's now all equal to 0. That's my denominator factor or quadratic. You can hopefully see then that these cross terms result in 0. We have plus j8 times s plus 6 and a minus j8 times s plus 6. And we're left then with the quantity s plus 6 quantity squared and a minus j squared times 8 squared. But a j squared, remember, j is in electrical engineering, that's the square root of minus 1. We now have, when we square j, we obtain minus 1. So minus a j squared gives us a plus, and that's where this structure came from that I originally wrote down when I said, oh, we have a quadratic factor. It's now s plus 6 squared plus 8 squared. So if you have a complex set of roots, you can write them in this nice structured way to explicitly identify the real component and the imaginary component of that complex pair of roots. In this case, our roots were at minus 6 plus and minus j8. Now we can also write that quadratic form in another way by multiplying things out. And if we do that, we now square the s plus 6. That leads to s squared plus 2 times 6 times s plus 6 squared plus 8 squared. And now I've conveniently made this 3, 4, 5 triangle just in a scaled manner. I now have a 6, 8, 10 triangle. I'm hoping you're starting to see a lot of these pieces fitting together. And so 6 squared plus 8 squared, Pythagorean theorem tells us that's 10 squared. So now we have our quadratic, not written in this sort of factored form that explicitly shows the real and imaginary components, but now it's written in a s squared plus 12s plus 100 form or structure in a maybe more traditional way of expressing a quadratic. Now the standard form, another way of writing that is to write it as s squared plus 2 zeta, that's a zeta, omega sub n s plus omega sub n squared. Omega sub n is the natural frequency. That's how the system would like to vibrate if there was no damping. It would vibrate at a frequency of omega sub n. With zeta, the damping ratio, that actually moves us a little bit into the left half plane. If we had zero damping, if zeta was 0, then we would just have s squared plus omega sub n squared, and we would end up right on the imaginary axis with poles at plus and minus j omega sub n. That's the natural frequency. We actually are generalizing that so that we can move off the imaginary axis. Our poles are not always on the imaginary axis, and we're identifying omega sub n and zeta in this quadratic form when we've normalized the leading coefficient to have a value of 1, or we've made that a monic polynomial. So s squared has as its coefficient 1. What you would do then, if you're given a generic quadratic, you would first factor out the leading coefficient on the s squared, force that coefficient to 1, and then you can start identifying the natural frequency and the damping ratio if that quadratic has complex roots. So now if we compare the terms or coefficients between our example, which was s squared plus 12s plus 100, with this standard form of s squared plus 2 zeta omega sub ns plus omega sub n squared, we can now identify the natural frequency and the damping ratio for our particular example. In our case, we can then see that the natural frequency squared is equal to 100, or now omega sub n We can easily take the square root of 100. That's now 10 radians per second. That's our natural frequency in this particular example with that quadratic factor. And the 2 zeta omega sub n, that's all equal to 12. With that being equal to 12, we can then say, oh, zeta omega sub n is now 6. And we've already found omega sub n, so let's divide that out. And now we have zeta is 6 over omega sub n. Omega sub n we just found, that's 6 over 10. Or now zeta, which we will find, is between 0 and 1. And in this particular example, it has a value of 0.6. If you look at what we have here, hopefully you're starting to see that this 6 was the magnitude of our real part of our complex poles, and omega sub n is actually the hypotenuse of this right triangle formed by the real part and the imaginary part. And if we plot that, this is now what we see. In the complex S-plane, we're now using the horizontal axis is the real component of S. The imaginary axis is the vertical component. We can now put our poles for this quadratic factor, locating those at -6 plus J8 and -6 minus J8. Now I hope you can start to see that, oh, we have an adjacent side of 6 in length, a vertical of 8, and we now have this hypotenuse, which is 10 in this particular example, or 6 squared plus 8 squared is omega sub n squared. And that's how I want you to start thinking about these these complex poles or zeros when we have a quadratic factor. In this particular course, I can't emphasize that enough, this is not really the correct Bode plot, but it's an approximation and it gives us a way to quickly sketch. And this is to simplify our sketching. What we are going to do is, starting with whatever poles we have, and we may use the notation of the real part in the left half plane being at minus sigma. The imaginary part is now at some location omega sub d, or we're now saying let's now look at poles, in this case they could also be zeros, as being located at minus sigma plus and minus j omega sub d. We know how to write that in the one form, that's s plus sigma quantity squared plus omega sub d squared. We can actually use some terminology or introduce some terminology. The sigma, I may refer to that as the damping in our quadratic factor. The omega sub d, now look, this is not the same as what we had above. Now we are isolating the real part squared and the imaginary part squared. The imaginary piece is the damped frequency. That's omega sub d. When you square that and add that to the damping squared, that's when you get the natural frequency. So if you now take this expression that we've been playing with, s plus sigma quantity squared plus omega sub d squared, the real part of the complex factor is given by sigma in magnitude, and the imaginary part is omega sub d. We can push that all through or perform those squaring operations, and we end up with what I've written in blue, where the damping is now the sigma and the damped frequency is omega sub d squared. If we compare that to the previous standard form of, in black here, of s squared plus 2 zeta omega sub n s plus omega sub n squared, we see the connection between the damping ratio, which was zeta, the damping, which was sigma, the damped frequency. Now I'm cheating. I'm just going to go from there, because that's the same term that we've used before, and here omega sub n is our natural frequency. You hopefully will start to get comfortable with this. The natural frequency is really just the distance those poles are, and we'll need this in the filtering section or unit. The natural frequency is the distance from the origin to those complex poles. Omega sub n is there, and omega sub n is there. And it's actually just the hypotenuse of a right triangle, where the right triangle now has an adjacent side of length sigma and a vertical side or opposite side of length omega sub d. And we have those two triangles in both the second quadrant and the third quadrant. Now, all of that said, what are we simplifying? Well, what we're going to do is it's a little more challenging to sketch with this imaginary component or having a zeta value. So let's go ahead, and for this class we are going to let zeta, the damping, be 1. I've already talked about what happens when zeta is equal to 0. When zeta was equal to 0, we've now moved our omega sub d up to having this omega sub n value. Now I want to move us down here where zeta is equal to 1, so that now instead of having complex poles, we're going to, in the sketching process, simply approximate that with 2 real equal roots. So in this particular form, we're just going to set zeta equal to 1. We're going to swing those complex poles around. We're going to just push them down, and now we are going to make this approximation in this class, so that now when we start seeing these complex poles, we can sketch those, or we will quickly simplify the sketch by making those have real roots, and we'll just now have 2 real equal roots at a value of what? Well, the hypotenuse hasn't changed.